523 623.
We rolling, we live. Okay, looks like we are live and we are good and we're streaming. Sounds good. Hello everyone. Welcome to the OneClass channel. My name is Millan and I am a third-year software engineering student at the University of Carleton. Today I'll be going over some commonly asked mathematics questions at both the high school and university or college level. If you need some help tutoring, check out the links in the description below. Okay, sounds great. So let's switch over to my screen and we can start doing some mathematic magic. Alright, so this is the first question that we're going to handle. The first question is, what is the integration of 1 divided by x? So to draw this out formally, I'll draw out, we are looking for the integration, whoops, let me get my pencil tool. We are looking for the integration of 1 divided by x dx. Okay, so we know that this is equivalent to the integral of x to the -1 dx. And we know that, the reciprocal is the same as raising something to the power of -1. Now, normally, we would do, we'd add 1 to the power and then have a coefficient in the front. But x to the power of -1 is a very special case where the derivative of this is equal to the natural logarithm of x, the absolute value of x, plus a constant of integration. Now, it's always important to have our constant of integration because let's say we want to take the integral again. If we don't have that constant, we're going to be in trouble. So we definitely need that constant here. Now, we know that we can check our work of our integration by seeing, hey, if the derivative is the same as the original, we're probably good. So let's do our double check. And we will do the derivative of natural logarithm of the absolute value of x plus c. So we'll do that by doing d over dx over this whole thing in brackets. So we have natural logarithm of the absolute value of x. I suppose in this particular case, the absolute value being on the inside or outside does not particularly matter. Plus c. So we know that by definition, the derivative of natural logarithm is 1 divided by what's inside, and then multiply that by the derivative of what's inside through the chain rule. So let's do that. So we have 1, these are equal to each other, so 1 over x multiplied by the derivative of x, which is like d over dx of x. That cancels out to 1, plus the derivative of c is 0. So this is just equal to 1 over x, because here we have 1. So we don't got to worry about that. And our result, after we took the derivative of our integration, we found that we have the same as our original, 1 divided by x. We know that the answer to the integral of 1 divided by x is definitely natural logarithm of x plus the constant, because we can never forget the constant when we're doing integrations. Now, why do we need the natural logarithm here, or the absolute value in the natural logarithm? Well, I'll scroll down here. Let's say we want to draw the graph of a natural logarithm. So we got our y-axis vertically, and we have our x-axis horizontally. I'll get a different color for this. Let's say red. The logarithm has a shape like this. And where it intersects at y equals 0, that is x equals 1. Because of this, and because the natural logarithm never is invalid for a negative x, like try taking the natural logarithm of like -5. It's not going to work out. So that's why we need the natural logarithm to have an absolute value on the inside, so that we can never get a situation where we're taking the natural logarithm of something on the negative side. Always hit it with the absolute value beforehand. So in our answer that we have here on OneNote, it's all looking that way. We do have the right answer, and we can verify the solution. So that's looking great. Let's leave a comment there. Cool. Good stuff. Okay. So now we have our second question. We have the derivative of cosine x. So we can rewrite cosine x as cos x, as it is normally. Whoops, let's get the pencil tool. So let's write this out in black. Cos x. So we need to find the derivative of this. So we got to do d over dx of cos x. Now, this is one of those derivatives that you're kind of need to gonna memorize. It really is just negative sine x. Keep in mind, this negative, never forget. If you forget that negative, you will be in trouble, and we definitely don't want that. So a nice thing about sine and cos is that if you keep differentiating it again and over again, you're going to see like there is an alternating pattern between like it goes from cos to sine, sine to cos, cos to sine, sine to cos. Like this pattern of differentiation is going to repeat itself. Of course, you got to consider like incorporating the negative sign in front and that coefficient, but the derivatives and integrals of sine x and cos x in general are fairly straightforward, because you know that sine and cos are related through their derivatives and their integrals. Just make sure that like the derivative of cos is negative sine, and you remember that negative always. So yeah, this question is confirmed here on OneClass, so that's good. And yeah, so that's that. Cool. Okay, so we have our next question, which says, how do we convert between polar and rectangular coordinates? So we do have a moderately easy way to convert between them. But first, let's explain what is the difference between polar and rectangular coordinates. So rectangular coordinates, we are normally pretty familiar with them, like our xy. I'll draw out something like that to just show it. So check out this. This would be like the y-axis. Perpendicular to that, we'll have our x-axis. And let's say we have a point A here, and it's at position like x of A, y of A. We would see like it would intersect with the y axis at y of A, and it intersects with the x axis at x of A. Fairly straightforward stuff that we are most likely already familiar with. Now, polar coordinates are a little bit different. So we can draw out our same axes here, but we don't necessarily want to label them x and y. Let's say we have point A here. You want, instead of x and y coordinates, we have our points defined by an r value and a theta value. The r value corresponds to the radial distance. And the theta value corresponds to angle. And you do need to define our like 0 angle point. So let's say this horizontal axis here is going to be our 0 angle. So you see how A is defined like, okay, first we go, you know, a certain direction amount along the x-axis. We'll call that XA. And then we got to go up in the y direction by a certain value y, A, to find our point A. Here we're going to do something similar, except first we're going to find our angle. So just to show this like visually, this distance here, that's r. That's the radial distance away from the origin. So I'll just draw that out. Origin, like where we originate from. That's a nice way to remember that. So we have our r, our distance away from our origin. And then we have the angle that it makes, which is theta. Okay, so the secret sauce to the conversion between rectangular and polar is, first we got to know that it is always possible to convert between polar coordinates and rectangular coordinates. We just need to find the conversion. Now you see how, just looking at this, it does have a triangular-like shape. Let's say that this is A. How would we find the coordinates of A? Well, if we look at the r, this is basically the hypotenuse of a right angle triangle with like its two short ends, like the adjacent and opposite sides, not the hypotenuse. Basically the perpendicular parts of this triangle are the x component and the y component. So to find the length of r, which is just the hypotenuse, we're basically going to do Pythagoras' theorem. So we know that r is the hypotenuse, right? And Pythagoras' theorem says that the hypotenuse squared is equal to the perpendicular parts of the triangle squared and added together. So this would be like x squared plus y squared. Let's isolate for r on its own. So without the r squared part, we can just make that r is equal to the square root of x squared plus y squared. Cool. Now, should we worry about plus minus? Yes. In general, you should assume that your r is positive. Sometimes if you'll get it negative. Some questions will ask for that. If, for example, we have like theta has the angle this way, if r happens to be negative, that just means that we're going in the opposite direction. Okay, so the angle would be the same. It's just like instead of A being here, it would be around where origin is written. But in general, like you want to be able to look at your graph and specify like r. In general, you want r positive, and then you specify which quadrant it is in with theta. But some people do it either way, so stay ready for both. Okay, so we found r. Nice. How do we find our theta? Our theta value is the angle that our r makes with like our 0 degree axis. How do we find that? Well, in a similar way to how we found r based on the knowledge that this is very similar to a right angle triangle, we can also find theta knowing that this is extremely similar to a right angle triangle. So let's say we have a triangle like this. I guess we did find r, and this is our y, and this is our x. That's our theta. We could use theta to calculate it, but I mean, we could use r to calculate theta, but I feel like it'd be more direct if we're trying to go from polar to rectangular to use x and y. So we know with our lovely trigonometry knowledge that the tangent of theta is equal to the rise, the y, divided by x. So let's say we want to isolate theta. We'll just take the inverse tan of both sides, and that will cancel out the theta on the left side, and we'll have the arctan or inverse tangent on the left side, and that will give us our angle. So theta is equal to arctan or inverse tan. Different names, same thing, but you know, be ready for both, of y divided by x. That is super cool. So now we have our r like that, and we have our theta like this. So this would be how we go from, like, if we're given x and y and we're starting in rectangular and we're going to polar, well, we just take our x and y values, stick them in this equation to get the r, stick them in this equation to get the theta, and then we're good. If we are given our polar coordinates, like if we're giving an r and a theta and we have to find its rectangular equivalent, we would just do the same process in reverse. So you would like do regular tan to both sides, and then you would have a ratio for x and y. And then here, like, you would square both sides, and you could solve for x and y individually. It's fairly simple. How about we run through an example? Let's say we want to convert the point 3. So like this is x, and 4, and this is y. So this is rectangular. Rectangule. Okay, and let's convert it to polar. So we know our polar equivalent is going to be like r theta. We know that r is equal to this. So we have our x squared plus y squared, all under the root. And our theta is inverse tan, also known as arctan, of y divide x. Okay, let's sub in our numbers. We have 3 for x. So we have 3 squared plus y is equal to 4. 4 squared. Okay, and our inverse tan is 4 divided by 3. Okay, so 3 squared, that's 9. 4 squared, 16. 9 plus 16, 25. Square root of 25, that's 5. So we're going to have an r value of 5. And what's the tangent value going to be? Well, mental math of inverse tangents is a little more difficult. So I'm going to pull out my handy dandy calculator, And I'm going to do the quick calculation of inverse tan of 4 divided by 3. It's about 53 degrees. 53.13 degrees. Sometimes you'll need to do this in radians. It really depends on what type of applications you're using this math for, but be ready for degrees and radians. Of course, like converting to radians from degrees is not particularly difficult, but just know that you really got to be ready for both. So a 53 degree angle would look something like this. And this distance would be 5. Now, does this make sense? Does this line up with a point 3, 4? Like we would go 3 along the x direction and then 4 upwards? Yeah, it does make sense. So to convert between polar and rectangular, use these very special equations. The radial distance, x squared plus y squared. Put them under the root. That will give you the radial distance. Beautiful. And then for the angle that it makes, just take the inverse tan, also known as the arctan, of the y component divided by the x component. Super cool. And this will be very useful for some pretty advanced math stuff, but you know, it's good stuff to know. I guess another thing to add that I guess we see here in this is to go the other direction. Let's say you're given let's say that you're given the polars and you want to go to the rectangular. Well, we have special equations that help us do that. So we know we have like x is equal to r multiplied by cos theta. And we have y is equal to r multiplied by sine theta. Now, why does this work? Well, let's say we have a situation like this. This got a length of r. It's got an angle theta. Like this right here would be its x component. This is really just why it is cos is like cos is the relationship between the hypotenuse and the side that is adjacent to the angle. You multiply the hypotenuse with the value that cos gives you for the angle, and it'll give you the x. Makes perfect sense. And the similar thing for the y. Sine is the ratio between the hypotenuse and the opposite. You see opposite, it's on the other side of the angle. And that's just like the ratio between them. We multiply them by the actual value of the hypotenuse, and we will calculate y. So these are also key equations if we want to go between polar and rectangular. These two equations, as well as these two equations. And it would seem like the answer or the solution that is given on OneNote is already or agrees with us. So we can say that the above solution is correct. Good stuff. So that would conclude this question. Okay, cool. So the next question I would like to cover is this. We got to find the missing number in this sequence, or I guess series of numbers. So first we got 9. I'll just rewrite it here. We got 9. We got something. We don't know yet. That's what we got to figure out. We got 6,561. And then we have 430, 467, 2, 1. So we're trying to look for the missing number. But to find the missing number, we first kind of got to know, what's the pattern? How do these numbers relate to each other? Well, my preferred strategy for looking for patterns like this is we want to have like two terms that are like close to each other, or like immediately after each other. So in this case, we got the 65, 61 followed by the 4 million term. Yeah, don't need to worry about reading that out. Okay, so let's see. We're probably not going to be doing addition between terms because like we're going from 6,000 to 4 million. Like that is a jump that is large to the point where it's unlikely that we'll be adding. So most likely we're going to be multiplying by something to get there. So let's divide these terms. So we're looking for what multiplies. What multiplies 65, 61 to get to 4.3 million or so. So let's do that division. 4304672 divided by 6561 is equal to something that I'll figure out with my handy dandy calculator. Four, 6, 7, 21 divided by 6561. And the answer is 6561. That's a familiar looking number. It's almost like maybe the rule is that the current term is the previous term squared. If that was true, that means the missing term would be 9 times 9, and the missing term would also be the square root of 65, 61. Is that the case? Well, let's find it out to see if like the actual rule is like current term is the previous term multiplied by itself. If that was the case, it would be 9 squared is equal to the square root of 65, 61. Because like if to go forwards in the pattern, we're multiplying it by itself. And to goes backwards, well, we'll do the opposite of that, which is taking the square root. So 9 squared, thinking back to my times table, that is a solid 81. And pull out the handy dandy calculator again. The square root of 65, 61 is 81. Hey, would you look at that? That means 81 squared becomes 65, 61. So our missing term in the pattern is 81. So to rewrite the pattern, we got 9, 81, 6561, and then 4,304,672. Whoops, that's not even 4 million. That's 43 million. Maybe I shouldn't draw those commas because they can confuse us with the commas used to separate our terms, but that would be our final answer for the sequence once we find the missing number in the series. Super cool. And it would seem that the solution that we're given agrees with us. So I got to verify that solution by saying the above solution is correct. Nice. So So that allows us to move on to our next question. Okay, so our question here, what is the derivative of sine, but the argument of sine is x multiplied by 2? It's really just asking us to do this. Sine times 2, or sine of 2 times x. Okay, so the first thing that we're going to need to recall before we handle this is the chain rule. If you forget the chain rule, you're going to be in trouble. The chain rule is that when you have a function, like in this case, or we have a composition of functions and we're taking the derivative, in this case, like we have sine x, or we have 2x that is passed to sine x. So we have a function result as the input to the next function, sine x. The result of 2x becomes the input of sine x. Whenever we see something like that, we're going to need the chain rule. So the chain rule just means that we're going to take the derivative normally, but we also need to multiply that whole term with the derivative of what's inside, also known as the internal derivative. So the internal derivative in this case is d by dx, which means derivative. Sometimes you'll see like, like originally you have function and then function prime, but d by dx also means derivative of 2x. That's just equal to 2 because, with our rule, we subtract the power by 1. Here's x to the power of 1. Subtract it down to like x to the power of 0. That becomes 1. You multiply the whole thing by 1. It remains 2. So the result of this is 2. That's the internal derivative. So we need to do that is equal to, well, what's the derivative of sine? The derivative of sine is cos, positive cos. So let's just put that in as a positive cos. When you're doing the chain rule, like your external derivative, you keep the inside the same. So 2x stays the same, but you multiply with the internal derivative, which in this case is 2. Comes from there. So let's rearrange this to make this a little bit more beautiful. Here is just to be formal, but we can remove that now, and we can just move the 2 into the front. So we have 2 times cos 2x. That is the derivative of sine 2x. And this is our final answer. The only place that I feel like is a likely place of possible errors is perhaps forgetting to multiply the internal derivative. So make sure that you're really sharp and comfortable with the chain rule and that you will never forget to multiply the internal derivative, because if you do, your final answer will be wrong, and that's certainly something we do not want. Cool. So the solution that we see on OneNote is definitely the solution that we just calculated. So we can verify that the above solution is correct. Super. That's very nice and handy. Okay. Our equation, or our next question, is what is the derivative of tan x? So to translate this sentence into an equation that we can handle, we'll have d over dx of tan to the x, or tan of x. What is that? Well, this is something that you might want to memorize, but I'll explain it more deeply as to like why this works out. So the answer to this is secant squared of x. If you're not familiar with secant, this is equivalent to 1 divided by cos squared x. And if you're not familiar with like this right here, the power on the cos, that is equivalent to like 1 over the entire like cos of x. Like that entire thing is squared, which is what it means by like having the power here. Okay, but let me explain why. So an important thing to know about tan is that tan of x is equal to sine of x divided by cos of x. That is a pretty fundamental trigonomic identity that you're going to want to know. Is that sometimes in your equations you might see tans. It could be difficult to deal with. So if you substitute out it with a sine x divided by cos, sometimes it can make things easier to simplify. But taking the derivative of tan x is the same as taking the derivative of sine x divided by cos x. So let's see how that works out. D over dx of sine x over cos x. So how do we handle this? We need the quotient rule. Because we can't just like take the derivative of the top and then derivative of the bottom and then expect it to be good. That's not going to be the right derivative. We need to do the quotient rule. What is the quotient rule? Well, let's run down the general formula for the quotient rule, and then we'll use our general formula, input in our specific case of sine x over cos x, input that into the general equation, and then we could see the general equation in action. Because the quotient rule is a very important thing in calculus that you will definitely need for anytime you're doing a derivative of a fraction where the top and bottom are both functions. So the quotient rule is as follows. D over dx of, let's call it the top function, let's call that f of x. The bottom function, let's call that g of x. So the answer to this is the derivative of the first one, or the top one, f of x, multiply that with the natural bottom. Subtract the natural top multiplied by the derivative of the bottom. You see how these are kind of like vice versas of each other? Derivative of the top, like only one of these is going to be derivative, and the one that it is, is opposite for both of these. It's kind of a nice and easy way to remember it. Okay, that's going to be the top of this little fraction, and the bottom is just going to be the natural bottom, but you got to multiply it by itself, so square that guy. Okay, so this is the general formula for the quotient rule whenever we're taking the derivative of one function divided by another function. So let's, this is our general formula, so let's input our specific case of our top being sine x and our bottom being cos x. So in this case, our f of x equals sine x. Derivative of this, f prime x, equals positive cos x. What's our g of x? Our g of x naturally is the bottom part of here, so that's cos x. And let's take that derivative, g prime of x. What's the derivative of cos x? Negative sine x. If you forget the negative, very bad time you will have. Okay, so let's fill, now that we got these, we could fill in this whole thing. So let's do that. So we're doing originally is dx of tan x, derivative of tan x. As shown here, it's the same as derivative of sine x over cos x. So let's input our stuff in the box into the general quotient rule formula. So we got f prime cos x multiplied by the natural of the bottom, which is just cos x. Oh, let's just square the cos x, because it's just cos x times cos x, right? Cool. Minus, we have the natural top, so that's sine x, multiplied by the derivative of the bottom, which is negative sine x. So we're going to multiply the negative sine x into this. That negative plus this negative, those two together, negative times negative becomes a positive. So this becomes positive. And that entire sine x thing becomes squared, because we have g prime multiplied by f, sine times negative sine. The result of that is negative sine squared, but originally we're subtracting, so it becomes positive sine squared. Cool. And the bottom of this whole equation is the natural original bottom, but we got to square it. So we're going to take our g of x, cos of x, and we are going to send it to the square. We're going to square that. Cool. Now, a fundamental trigonomic identity that you are probably going to use a lot in your mathematic magic is that 1 is equal to cos squared x plus sine squared x. This is a super important identity. This identity will save your life in many places, and this is one of those places, because you see how the top is well, you know, you bring that square, you can put it on the cos instead. That's really equivalent to this. Same with the sine. The entire top is this, so the top of this fraction is really just equal to 1 over cos squared of x. Hey, would you look at that? This is equal to what we said it was originally. We originally said that it's equal to secant squared of x, which is equal to 1 over cos squared of x. So, wow, would you look at that? We just proved that the derivative of tan x is 1 over cos x, or 1 over cos squared x, which is equal to secant squared x. Sometimes it's easier to write secant squared x, but some calculators don't even have a button for secant. So for those situations, like, you want to rewrite it as its reciprocal, 1 over cos squared. But once you do that, you got the derivative of tan x, and you could be like, thanks, like tan x, thanks. You'd be like, yeah, super cool. We got the derivative. We living good. We feeling good. Breathing good. Yeah. So our answer here, that is on OneClass, we got secant squared of x. Looks about right. That's great. So let's leave a comment saying the above solution is correct. Super cool. It is correct, but maybe if we add some more detail, it could help us understand this concept much deeper. But that would conclude this question. Cool. So our next question that we got to cover is find the equations of both lines that pass through the point 2, -3, that are tangent to the parabola y equals x squared plus x. So let's dissect what we need to know from this question. So original function equation is y equals x squared plus x. And the point of interest, let's call that P, and that is at 2, -3. So that's the x value and that's the y value. We're going to be dealing with rectangular coordinates here. Okay, so we got to find the two tangent lines intersecting with point P. Okay, so first let's do a little analysis of what we're going to see on our original function equation. So we see that the leading coefficient for the x squared term is +1. Since it's positive, we know that this parabola is going to be opening upwards, kind of like a cup type shape or a U type shape. So something like this. We're going to have a point P somewhere. This is just to get a rough idea. We don't necessarily need like super detailed diagrams. But you see how we're going to have two tangent lines that intersect with this. One of them is going to be like on this side. I'll draw that, like, maybe I'll start that from here to show that it, like, one will be from this side. Will be like a negative sloping type of tangent line. And the other one will be like pretty vertical, but like you know, like the parabola would keep going, and then somewhere up the parabola there would be some point where the tangent line does intersect with this. So we are definitely going to have two lines that intersect with it, only two lines. So yeah, cool. Let's find those lines. So we know that like y is equal to x squared plus x. To find the tangent line at a certain x position of this, we need to find the derivative, right? So let's find the derivative of y with respect to x. So let's call that y prime. Y prime, well, the derivative of this, we bring the 2 down, we subtract 1. So we got 2x for the first term, 2 times x. The second term, the derivative of x on its own is just its coefficient, which is 1. So 2x plus 1. Super. Now, we know that the line that's going to intersect, like be tangent to the parabola and also intersect here, we know that you can find the slope of any line if you have 2 points in that line. So let's say we have this point, or it could be that one, but I'll just focus on this one here. Let's say that we have like, this is like AB. Knowing point AB, or knowing point with coordinates AB and knowing the position P, we can find the slope there. And the slope on that connects those two has to be identical to the slope that we have on our derivative, right? Because the tangent point at this point is going to be a slope with a certain, or is going to be a line with a certain slope. Okay, so let's find the slope between any point on the parabola and point P. So we know that like AB is going to translate to like x for the x coordinate, and then the y coordinate is going to be x squared plus x. That's the legitimate formula for how we calculate our y coordinate given our x coordinate. And then our point P has coordinates. The coordinates are 2 on the x and -3 on the y. So let's find the slope between these points. Of course, this one is not an actual point, but this gives us any and all points that are on the graph. slope between the points. Okay, so the definition of slope is rise over run. Rise is like y2, the second y, like its destination, minus the y component of its starting point. And we got something similar for our x. So we have the x part of our finishing point minus the x of the initial point. Let's sub in our points here. So our second point, like let's say we're looking at this one, we're starting at to the left of point P and then we're going down to the right. So let's say like this is our y, like this is our x1, this is our y1, and these will be like our y2 and our x2. Okay, so let's sub those in to our little equation. So for y2 we got negative 3. Here we have 2. And then we're on the top, we're subtracting x squared plus x. And on the bottom, it is just x, which is the departure point. Okay, so this is the slope of the point of interest P with a point there. But that slope has to be equal to the derivative for it to be a tangent line. So how about we just set this whole thing equal to 2x plus 1, which is the derivative. Okay, with some quick maths, let's expand this all out. Equals negative x squared, because you see the negative here multiplies into the x squared and is also here. So it's negative x squared minus x minus 3. Wow, the top is very negative, but that's nothing to be worried about. And the bottom is 2 minus x. Okay, let's multiply both sides by 2 minus x to get rid of this denominator, put it to the other side. So we got 2x plus 1. And we have 2 minus x. Then we have minus x squared minus x minus 3. Okay, cool. Now let's expand out the left side. So we have 2x times 2. So that's those two. And we got 2x plus 2x times minus x. Then we got plus 1 times 2. And then we got minus, or we got plus 1 times minus x. Equals this. But I'll clean this up to make this easier to read. So this is the only x squared term. So we're going to have negative 2x squared. Combine the x terms, so we have 4x and then minus x. So that's going to be plus 3x. 4 minus 1 is 3. Sounds about right. Plus 1 times 2 plus 2 equals negative x squared minus x minus 3. Looks like we could simplify this down to a single quadratic that we can solve for x. So how about we do that? Let's set the left side equal to 0. Then we're going to have to add 2x squared to both sides, so that's going to be positive x squared. Subtract 3x from both sides, so that's going to be negative 4x. And we're going to subtract 2 from both sides, negative 5. How do we figure out what x this is. It's hard to factor it out because, you know, the last digit here, 5, that's a prime number. So we're going to need to use a quadratic formula. Actually, no, never mind. -5, or, okay, I'll write out what I'm trying to say here. So we have like x minus 5, and then x plus 1. That's what I mean that we can get this. So essentially to get here, we need to find 2 digits that multiply to get -5 and add up to -4. That would be a combination of -5 and 1. Multiply them together, you get -5. -5 plus 1, that's -4. So these two are equivalent to each other, which means that our points of interest are x equal 5 and x equals -1. These points have tangents intersecting P. Okay, but the question says we need to find the equations of both the lines that intersect with the point P. So to find out where those tangents are, that's not enough. We need the complete equation of the tangent line. So I'll slide over here to just get a little bit more space. Our original question is, or our original equation, y equals x squared plus x. We are basically now looking for tangent line equations at x equals 5 and x equals -1. So to find the tangent line equations, that's fairly simple. It's just we had to find the x equals 5 and x equals -1 originally. And we did that through the process here. I'll review that at the end. Okay, cool. So to find the tangent line equation, given this, first we need the derivative. We already calculated that previously. Y prime is 2x plus 1. So how about we sub in x equals 5, y prime of 5 equals 2 times 5 plus 1, which is 10 plus 1, 11. Beautiful. Okay, so we know that we know that's the slope at x equals 5. Cool. So we know equation of a line. That is y equals mx plus b. Also, we have a point P, which is 2 and -3. Okay, so we can use the point P to sub in for our y and our x. We found our m, which is our slope. That's 11. We just need to now solve for b. So once we sub in everything, b is the only unknown, so we can easily solve for that. Let's first isolate b. So b is equal to mx minus y which is equal to 11. Multiply that with 2, and we're getting that from point P. We're subbing in point P, 2 for x, negative 3 for y, minus negative 3. B, 22, I don't know about you, I'm feeling 22, plus 3 base is 25. Okay. So equation of this line would be y equals 11x. Oh, oops. See, this should actually be negative 25. You see here, I rearranged wrong. This should really be my bad. I'll clean it up. You know, mistakes can be made sometimes. Just don't repeat them. Mistakes don't make you dumb. Repeating mistakes makes you dumb. So this is actually y minus mx. So y we had negative 3 minus 11 multiplied by x, which was 2. So we got negative 3 minus 22, and that is negative 25. So our b is negative 25, and our equation here is 11x plus b, and b is minus 25, so we'll just put that here. One of the tangent line equations at x equals 5 intersecting at point 2, negative 3. Okay, so that would be one of our final answers. So we did for x equals 5. Now let's handle the case when x is equal to negative 1. So we're largely going to follow the same method that we did for x equals 5. So we're first going to do y prime with a negative 1 for x. So our y prime equation is 2x plus 1, which is equal to x is equal to negative 1 in this case, plus 1. So y prime of negative 1 is equal to negative 2 plus 1, negative 1. So that is slope at x equals negative 1. We know equation of a line. That right there, y equals mx plus b. Isolating for b, because we know y and x, that gets subbed in from our point here, 2 for x, negative 3 for y, and our m in this case is negative 1. So we just got to solve for b, and we'll do it correctly this time. Y minus mx, not the other way around, which I previously mistaked. Okay, so let's math this out. Y is equal to negative 3 minus negative 1 times the x, which was 2, comes from point P. Okay, so we got negative 3 plus 2. B is equal to negative 1, which would mean that our equation here would be y equals negative, well, our slope was -1, so we just do negative x, plus b, our b is -1, so that's going to be -1. Cool. And this would be our second version of a other tangent line equation at x equals -1 intersecting at p 2, -3. Cool. How about we put these on a graph to confirm that we did this correctly? So I'm going to pull up on a new slide here. I'll do Desmos. Pull up the graphing calculator, Desmos. Gotta love Desmos. Graphing calculator. So let's put our first tangent line equation in. 11x minus 25. Our second equation, minus x minus 1. Hey, let's see if they intersect at the point 2, -3. Oh, would you look at that? Would you look at that? That's cool. Our original equation was x squared plus x to the power of 2 plus x. That looks pretty tangent to me. And it's intersecting at our point of interest. So the blue line, y equals -x, -1. That looks pretty good. Our red line corresponds to 11x minus 25. Hey, that looks pretty tangent. It looks so tangent that they're basically on top of each other. That's encouraging. It also intersects at the point of interest, 2, -3. The green is our parabola. That's what's inspiring our tangent lines. And wow, it seems that we have a complete answer for this question. We have our two equations for the tangent lines to this parabola that intersect with our point of interest, 2, -3. So when we look through the solution here, well, the solution is incomplete. We have the derivative, which is an important part of this. But finding the derivative is the first step. Then you need to consider, the derivative is going to give us the slope. And we need that slope to be equal to the slope that we would get if we were to like make a line with a point on the parabola and the point of interest P. Those slopes have to line up. So we made our point on the graph, which is just x, and then its y component, which is x squared plus x. That's the equation for y. And our point P, we found the slope between those two by doing, we treated point P as our destination and our starting point as like the point on the graph. And we used our slope equation to slide that in. We equated our calculated slope between P and the point on the parabola. We made that equal to the slope that we would get from the derivative, 2x plus 1. Since they were equal, we can do some rearranging, some mathematic magic, expand them out, multiply them together, make them a single quadratic, make it equal to 0. We could have used quadratic formula. It's perfectly valid to use quadratic formula, but sometimes you get nice numbers like this, like -5 and -4, so we know that we multiply +1 or x plus 1 and x minus 5, that will give us this. Try it out. I bet you'll get it. That tells us that the points of interest that give us tangent lines that intersect with point P, point of interest P, 2, -3, those tangent lines occur at x equals 5, x equals -1. So that transforms, once we know those, that transforms the question into find the equations for tangent lines at x equals 5 and x equals -1, knowing point P and knowing this. So we find the derivative, and then we found the equation of the line, by first finding the slope, subbing in a point for x and y. We use point of interest p, but if you did not have a point of interest p, you could just use like the actual equation to solve for a point here. Like you would solve in any x, or the x at that particular point, as well as the y at that particular point you would need to solve for it. We solve for our base values, our b values in our equations of a line. Once we have that, we can finish and finalize our equations for the tangent lines that intersect with our point of interest, 0.2 and -3. And that is our complete solution to the answer to the question. Find the equations of the two tangent lines that pass through the point 2 and -3 that are tangent to the parabola x squared plus x. Sounds groovy, super groovy. So a comment on the solution is that the solution is incomplete. Need to use the derivative to equate to the slope of an arbitrary point. Arbitrary. Yep. Good thing I'm teaching math instead of spelling. Not economics either for selling, but yeah. For the slope of an arbitrary point and 0.2 -3. This will lead to a quadratic giving x values for where the tangent lines will intersect with 0.2 -3. Then solve for the equation of the tangent line at those x values solved for earlier. Looks good. And that would conclude this question. Hold up. Wait a minute. Did I answer this question already? Yeah, I think that answered all the questions that I had planned out for this session. Okay, so those are all the questions for today. And if you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and the notification bell below. If you'd like to submit your own question, visit the links in the description. And remember, if you like the video, definitely leave a like and leave a comment if you have something to say about it. Please share this video with your friends if you liked it. And this has been Millan Wang with OneClass, and I hope to see you soon. Bye now. Have a great day.